Yelling.
All right. Hi. So stress is force per unit area, and strain is elongation per unit length with no final unit, and it can be assessed either using tensile or compressive forces. And then we get the stress-strain relationship, for which we have the linear elastic region with a proportional increase in strain as we increase stress, up to a yield strength, at which point the material starts to develop plastic deformation or yielding, and finally failure. So just because you're probably already bored from that first slide, this is just an old question, but it's just a true-false question if you guys want to. So I'll go through some of the parts of it and then come back through it. So the first one is ductile materials undergo plastic flow, true or false? True. Yeah. Brittle materials fail in tension at high strain. Anyone? No? Elastic materials demonstrate permanent strain, and so B was false, which we'll go to, and elastic materials demonstrate permanent strain, true, false, sorry. Ductile materials when compressed show increased stress, true, and stiff materials are tough, true. So going back through that graph, the modulus of elasticity is the stress per unit strain in the linear elastic portion of the curve, and the Young's modulus refers to the modulus of elasticity in the tensile, when using tensile forces. The strength of the material is that which a material can withstand without deformation, which then goes through the yield strength, the ultimate strength and failure strength on the stress-strain relationship. And necking is noticed in the vicinity of ultimate strength, where there's a reduction in cross-sectional area associated with tensile stress and lateral contraction. Stiffness is defined as, is determined by both the modulus of elasticity and the dimensions of the material, and hardness can be assessed using a range of different scales, which effectively is looking at scratch resistance of materials. Fatigue strength, or also known as the endurance limit, is the stress at which the material can withstand stress cycles, and this is probably a more clinically relevant assessment. And finally, toughness is the amount of energy per volume that a material can absorb before failure hits the area under the curve of the stress-strain graph. And we can define materials further into ductile or brittle. And so ductile materials undergo plastic deformation before failure, but brittle materials exhibit very little plastic deformation before fracture. And so that was all with loading, but when unloading, material can be described as elastic, partially elastic, or plastic, with elastic materials returning to their original dimensions, but plastic flow being material that undergoes an elastic strain. So there's a range of commonly used materials which we did cover a lot of last week, so I didn't want to repeat that. But in trauma surgery, the majority that we use is titanium or stainless steel. And as we're aware, stainless steel is an iron-carbon alloy with the advantages of good ductility and strength, and obviously used in plate screws and nails. Titanium can be used as pure titanium or as titanium alloy, and the pure titanium produces the risk of being less ductile, so therefore providing less feedback to the surgeon, and therefore this screw breakage and titanium alloys have increased strength compared to pure titanium. And this is a table from a recent JBJ constructional course lecture, which I don't know if you can read the numbers there, but as you can see there, titanium has about half the modulus of elasticity of stainless steel, but if increased in thickness by a few millimetres can overall increase its strength to be comparable. Corrosion is an important concept when looking at different metals used in surgery. So because overall it can result in weakness of the implant and also release of corrosion products into the local environment. There are different types of corrosion. Galvanic corrosion is where an electrochemical potential is produced between two different metals and therefore creates a battery effect and migration of the metal ions. Chemical corrosion is a chemical reaction with the material within the environment, and fretting occurs with micromotion between two articulating components. There's also crevice corrosion and degradation. All these materials can be applied into different methods of fixation, overall plates, screws and nails, and just going through the basics of screw fixation, requiring appropriate thread size, and which is important and to allow self-locking and also to allow appropriate feedback to the surgeon for the appropriate number of revolutions. When looking at torque applied in screw fixation, 50% of the torque force goes into the friction, overcoming the friction at the screw head interface, and 40% goes towards the axial force, and 10% to overcome thread friction. With plates, we have our range of compression plates and tubular plates, which everyone is most likely already aware of, so I won't go through the details of that. And finally, with regards to bone graft substitutes, there's a range of different bone grafts that can be employed in trauma surgery, and overall the main mechanisms in which they promote healing is through osteogenic, osteoconductive and osteoinductive methods. So osteogenic process involves a bone graft that has living cells that are capable of differentiating into bone, such as cancellous autograft. Osteoconductive is a material that provides scaffold for bone healing, and osteoinductive provides biological stimulus to induce differentiation. And this is just going in a bit more detail into the different types of available materials. So with autografts, as I mentioned, provide a scaffold as well as the precursor cells and osteoinductive factors, whereas the ceramic-based overall provide an osteoconductive increase in healing, and different types of polymers can also be employed in osteoconductive methods to improve in trauma healing. So in summary, there are a range of different materials in orthopaedics that, but overall the importance of the biomechanical properties and an understanding of this is important before being applied to the clinical setting.